Ricardo, please tell us about the context of today's talk.
Yes, so it is my pleasure to welcome and introduce Dominik, who I've been following a bit on Twitter in the last couple of years. Dominik has a very strong background combining anthropology, psychology, and evolutionary studies between the Marburg and the St. Andrews University, and he's currently working with an old friend of the IMC, Richard McCarrith in Leipzig. And he's also very active in the Early Career Social Learning Researchers Association, which is these days a very important source of support for a lot of the people working in this field. The reasons for which we invited Dominik here is that he recently published a very thought-provoking and interesting paper called Dynamic Social Learning in Temporally and Spatially Variable Environment, and in which, in a sense, he takes a very old topic of research at IMC, which is social cognition, the way we process social information, and brings a more explicit anthropological focus on that in trying to investigate in which ways people adjust the way they use social information, balance it with personal experience, and how that changes the environment in which other people then make decisions, which I thought was a very nice way of closing the circle. And additionally, I would also like to, let's say, emphasize the fact that his work is exemplary in the fact that there is a fantastic combination of computational modeling where the mechanisms that they're hypothesizing are formalized and tested before running with participants in order to better be able to figure out which mechanisms could actually be at play. And all the data or I can't remember the data, but at least all the simulation and the analysis code is actually open, and I've had a lot of fun playing with that. So I strongly encourage you, if you're in this kind of research, to actually follow up on that. With this, I'll leave the word to Dominik. I'm very excited to hear what you're going to tell us.
I share my screen. Okay, so thanks very much, Ricardo, for having me. It's my first ever real invited talk, so I'm super excited to be here and share some of my research to you. So I entitled the talk Collective Intelligence and the Cultural Brain, and I want to tell you some more about the full process of going from theory, so first from theoretical modeling to data and then back again. And in that, I want to emphasize the whole process, so not just I give you the results that we found, but also just how it all proceeded, but also some of the problems and pitfalls we faced, just to give you an idea of how this research actually works. Yeah, so I want to tell you about a form of collective intelligence that lies not in our individual brains, but in the accumulated cultural information that surrounds us. Humans are these immensely adaptable primates. So while all other great apes still primarily live in the tropical rainforest where they first evolved, our species managed to spread out of Africa and now occupies a wider range than any other terrestrial animal. But at the same time, we are very homogeneous genetically. So we are, for example, much less genetically diverse than chimpanzees, for example. And we also lack the specialized genetic adaptation to live in such diverse niches. And then there is this big question of how do we do it? With the same brains, with the same genes, how do we manage to survive in such vastly different environments? And one very common answer is that we're just super smart. We're just much smarter than other apes. We have these huge brains. We can do a lot of individual problem solving, and that lets us figure out what to do in circumstances. And the story is, of course, appealing, and it's also rather self-serving to our species, but it cannot be the full story. Because humans, even in the simplest environments, cannot do the basic stuff on their own. They cannot do, they cannot find their food. They cannot defend against predators. We are always reliant on social information. So our evolutionary success does not only depend on individual problem solving, but on our special abilities to learn from others. So such social learning allows our species to gradually accumulate cultural information over time and develop well-adapted tools, beliefs, and institutions that are often causally opaque, so we don't really know what they're there for, and that are too complex for any individual to invent on their own. Yes, so these are all photos from different field sites in our department. Yes, just to give you an overview of the vast diversity of environments humans face. So it goes from the tropical rainforest to the Arctic, from small-scale communities to mega cities, and that's really remarkable compared to other great apes, which are basically an evolutionary dead end. In doing so, we regard culture itself as an evolutionary process. So already in Darwin's books, he often draws on similarities between different evolutionary processes. So he compares it to linguistic evolution, but over the course of the 20th century, evolutionary approaches have often been associated with racist politics, and because there was this very clear linear view of evolution, that evolution just means everything becoming better, becoming more complex, with at least with of course the Europeans at the top. But this is a very different approach. We just regard culture as an evolutionary process because culture has a trait variation. It has some sort of inheritance, which is just a social learning. We pass on traits among each other, and there's also selection on cultural traits. So some cultural variants are just more successful than others, or the carriers of certain cultural traits are more successful than others. And importantly, one implication of that is that cultural design can and actually often does arise without a designer. So it was the major insight of Darwin that biological design is there, and it is very functionally defined, but it does not need an external source. It can arise from purely natural processes. And I would say that for culture, it's the same, that also a lot of the cultural artifacts we face are not actually created by one single genius, but they often arise from distributed processes in large populations, where there are many, many small increments that then scale up over time and result in all this fancy technology that we see around us. So culture really is an emergent population level phenomenon, and it allows us to adapt to vastly different environments. And we want to understand how this process exactly works. So how the adaptive population level phenomena emerge from basic learning choices and interactions of individuals. So in my personal research, I combine formal evolutionary theory, collective learning experiments in the lab, and Bayesian modeling. And I want to give you a flavor of all these three parts. And I want to start with formal evolutionary theory. Seeing formal models, many people have an initial reaction that they find them kind of abstract, unrealistic, stupid, irrelevant, that they just ask, like, what does it even tell me? Because they are abstract and they abstract away from many, many real life details. But I would argue that that's actually one of the biggest strengths of theoretical modeling. First, models force us to be really explicit about our assumptions. So they're basically inference engines which turn assumptions we make into inferences. And they let us do it in a very, very rigorous and logical way. So it's basically like a thought experiment in philosophy or in physics, but how the assumptions are translated into consequences is governed by rules of logic and math and computer code, and not just by our flawed reasoning. So I think it's really one of the biggest strengths of models that they're so abstract because they allow us to see the core properties of a system and not just all the random irregularities. And models are also often used to predict stuff. So, and models can be insanely good. So on the right, it's just some very toy depiction of some deep neural networks that can be insanely good at predicting. And on the left, you can see this geocentric model where astronomers added all these epicycles, which is to match the model to the observations. And this model, although it's incredibly false, makes very, very accurate predictions. And it can still be used. And I will also focus on some predictive models later in the context of the experiment. But I also want to emphasize that one cool thing about models is that they can actually be understood, that we can actually know what they're doing. And that's just the really nice thing about simple abstract models, that we can identify some basic causal forces and then just play with the assumptions and actually understand how the different forces interact in producing some outcome. And that's incredibly rewarding, I think, and it's very important for science. But on a more methodological front, we can also say that models are a very important tool in preventing harking. So this is the hypothesizing after the results are known. Because if you have a formal model, you cannot just discuss away any result you'll find, right? You just have to stick with what the model tells you. And you need to be an insanely good modeler if you want to tweak your model post hoc to fit your observations. Yeah, so I want to introduce like one of the models I did for my PhD, which is called When Does Selection Favor Learning from the Old? Social Learning in Age-Structured Populations. And so there's this very basic old question of what makes culture or social learning adaptive in the first place. Many people thought it's just adaptive because it lets us acquire useful adaptive information without the costs of trial and error learning. So that was one of the basic assumptions at the time in the 80s. But then there was this nice model by Rogers, which basically showed that pure social learning, so just copying without any strategies, does not increase mean population fitness, because the adaptive value is strongly frequency dependent. So if you're the only social learner around and everyone else is tracking the environment, then of course it makes a lot of sense to learn socially, because there's a lot of social, useful social information to copy. But as the frequency of social learners increases, there are very few other individuals that track the state of the environment. And so there can be this maladaptive information cascades, because everyone else is basically outdated when the environment changes. And so at equilibrium, there tends to be a mix of individual and social learners with the same mean fitness of as a population of pure individual learning. So that means social learning can evolve, but it doesn't really do much for the population as a whole. But cultural adaptation, so I've talked a lot about cultural adaptation and evolution, but there is a lot more to a real animal. And especially our cultural adaptation is deeply integrated with our special life history. So we have this prolonged juvenile periods. Some people also say we have childhood as a new separate phase. But although we grow so long and take so long to develop, we have our species has shorter interbirth intervals, so we can have more babies in shorter amount of time. And we also have an extended post-reproductive lifespan, which is unusual. But still, most models, or basically all models of the evolution of social learning and the adaptive value of culture, treat cultural organisms more like grasses. So everyone gets born at the same time, then they learn, they reproduce, and they all die. So there is no age structure, there is no real life history. But if you want to understand how culture really works in real organisms, we need more theoretical work that includes age structure and demography, life history. And so this model is the first step towards that. But then as soon as you have age structure, there is also naturally the question of who you should learn from. And there are many different views across societies. So for example, in ancient Sparta, they had this Garousia, which is a council of elders, which was highly respected. But also in many East African societies, they have gerontocracies, which means that social influence is basically structured along age grades, and everyone attends to the older individuals. But then the other side, in Western societies, we often attend to our peers instead, because we kind of think that the old people are outdated. It's often not true, but I mean there is a grain of salt to it, because if the environment changes too often, then some people just don't update their behavior anymore. So that was another a question I wanted to investigate with this model. So I said before that in order to make inferences with a model, we need to make a lot of assumptions. And so this model assumed a large age-structured populations. Large just means that it's large enough so we can ignore drift. Of perennial organisms, that means that they could theoretically live on forever, and that live in a temporally variable environment. So on the right, you can see what age structure means. So individuals are divided into different age classes, but they each time step they can survive from one age class to the next, and all adult age classes contribute to reproduction, which fills in the first age class. The environment can take on one of a very large number of states and may change each time step. And if that happens, all previously adaptive behavior becomes non-adaptive. And now that's a very important assumption of this model. We assume that individuals are born as juveniles who cannot reproduce, but learn about the environment, and adults cannot learn, but have the chance to reproduce. I know that's a super strong assumption, but it basically represents the trade-off between investing in learning and reproduction. And I've also shown that we can weaken this assumption in simulation, and the basic trade-off is still there. So it's important, as long as we have some sort of trade-off between updating, learning, and reproduction, the basic results should hold. And so what we're turning now is we're basically translating all these assumptions into equations. And that looks scary at first, but that is just the only way of how we can translate our verbal description of the model into a mathematical engine that lets us do work and see what the consequences are of these assumptions. And I should have said it earlier, but if there are any questions, please just interrupt me at any time. There will be plenty of space for questions in the end, I suppose, but still, like, if there's anything unclear, just interrupt me. And so as the first step with this model, I just wanted to see how proportions of social learners depend on different things, such as how much social learning evolves. And I compare a situation with discrete generations, so without all this age structure stuff on the left, which is the original Rogers model, and my age-structured model. And in both models, as you would expect, there is more social learning if the environment is stable and if individual learning is costly. So that's not very special. But then I also wanted to see if age structure actually resolves Rogers' paradox. So if in a model with age structure, if then pure social learning would increase population fitness. And to do that, I just plot the population growth rate lambda at equilibrium for populations of social learners, which are the lines, and populations of pure individual learners, which are the shapes on top. And you can see nothing. So I was disappointed by that because I had the intuition that it would resolve the paradox for some reason I will discuss later. But that's the nice thing about models. You just do it, and then there are the shapes on the lines, and you have to say, okay, shit, I expected something else, but yeah, but that's a nice thing about it. Yeah, so also with age structure, pure social learning can evolve, and there is a lot of it, but it doesn't really increase the population fitness at equilibrium because we have this trade-off I discussed earlier. But then in the second step, I wanted to see what demography is actually doing in these models. So what's actually happening. And so I compared different scenarios where selection acts on fecundity, which means on reproductive output, or on viability, which means the chances of survival. And I hypothesized that through viability selection, age structure or demography might function as a second adaptive force, because as you grow old, you can only grow old if you have adaptive behavior, right? So if there is selection on survival, age itself might be a cue for having adaptive behavior. And it purifies the population because it filters out non-adaptive variants, and thereby it might also provide a second source of useful trait variation that social learners can benefit from. And that's also what you can see there. So with the population of pure individual learners, we have this increase over age because there is this trade-off of surviving until a certain age, but then also environmental change that renders individuals non-adaptive over time. But that's just a distribution over age classes. But what I was really interested in is how that would affect adaptation levels in the long term. And what I found was that you can see on the in plot H that only in the scenario with social learning and with this demographic filtering effect, we can have accumulative improvements in culture and in adaptation levels over time without any inbuilt accumulative culture. So it's still a basic Rogers model where you can just copy someone, but just through the demographic effect of this demographic filtering, which increases the quality of adaptive information in older age classes, we can have this cumulative improvements in learning. But still, this is of course counteracted because it takes longer to recover after a change in the environment, because there's just so much social learning going on, because there's a lot of useful information to copy. So in the long run, it doesn't improve the population fitness, but it still enables you to reach very high adaptation levels, and that go much beyond what individual learners could obtain. Yeah, and then we had this very basic question: when should you copy the old? And with some insane magic, Richard, yeah, he has an insane intuition with math. I mean, I can do simulation, but he can do real algebra. It's amazing. We reached this inequality, which basically says that you should copy the older of two individuals if the environment changes slowly, and adaptive behavior is hard to acquire as a juvenile, but it's very important to survival. And on the right, you can just see the region of parameter space when individuals should copy the older of two individuals. I then constructed individual-based simulations just to see how general defining is, because this inequality was just based on pure math. So I wanted to see how does it even function in evolutionary simulations. And surprisingly, I found very, very little amounts of copy the old bias. So if you focus on the bottom row, you can see that there is basically no bright yellow region, which would indicate a copy the old bias. And this is because in situations where the environment changes very slowly and there is a strong survival advantage, basically everyone will be adapted all the time. So it doesn't really make a difference what learning strategies you use. And on the other hand, there are regions in parameter space, especially in the temporal model, where a pronounced copy the young bias can be favored. And that's in situations where the environment changes quickly, but there is still a lot of social learning. So we can say that a copy the young bias can be something like a compromise between individual and social information use. But then once we introduce social learning errors, so if social learning doesn't lead to the successful acquisition of a cultural trait in 100% of the cases, then we can get a lot of copy the old bias, because then this whole effect of demographic filtering I described earlier can increase proportions of adaptive behavior in older age classes, and that then makes them preferable social models. Yeah, so what did we learn from this model? First, age structure does not resolve Rogers paradox, and that alone would have been very useful to me, because it really violated my expectations, which is the nice thing about models. But an interplay between cultural and demographic forces can lead to cumulative improvements in adaptation levels. And the merits of age-biased learning strategies depends on the relative strength of forces. So we had the rate of change, we had the difficulty to learn a trait, and we had the strength of selection. And the copy the young bias might actually be more widespread in animals than is currently thought. Are there any questions specifically about the model? I can see there is something in the chat. Yes, any question about that? Otherwise, I would continue with the more empirical part. Okay, so for the rest of the time, I want to talk about this collective learning experiment that Ricardo mentioned in the introduction, which was called Dynamic Social Learning in Temporally and Spatially Variable Environments. And so as he already said, we were interested in how individuals would dynamically weigh social and individual information over time in environments that have both temporal and spatial changes. And the paradigm looked like that. So in each round, 2 groups of 4 individuals had to identify currently optimal behavior by selecting one of 4 different options. So here we had the 4 crops. And at each point in time, there was one option with a higher expected reward. So it was a multi-arm banded paradigm, and payoffs varied stochastically from round to round, but there was always one option with a higher expected reward. Participants were told that both groups live on different sides of a river, that due to differences in the local ecology might be characterized by different optimal behaviors. So in this example, corn is optimal in region 1 and potatoes are optimal in region 2. And from time to time, individuals migrated between different regions. So every 5th round, one individual from region 1 switched group with an individual from region 2. And that forces them to adapt to different environmental conditions. And in addition to these spatial changes, which just occur for 2 individuals at a time, the environment could also change temporally. This is for everyone at the same time. You can think about this just like something like climate change. That's just some external factor that just changes what's optimal. So there were both temporal and spatial changes in the environment. In each round, participants could access different sources of information by moving their cursor over these boxes. So you can see in the bottom that the boxes, the information in the boxes was hidden at first, and individuals must move over their cursor, and then they could see the respective information. And we used mouse tracking software to know when and how long they access different sources of information. So they could see their own choices and their personal payoffs from the previous round. And so that allows for reinforcement learning, right? They show something and they see what the result was or how much they got out of it. But then on top of that, they could also see the crop choices of other individuals. So of the 3 other neighbors that are in their region, and they could also see their experience levels. But this is how long they've already been in the present region. And so we wanted to use that to simulate something like age structure, because of course we cannot really manipulate age, and also age wouldn't be a valuable cue in this experiment, but it functions as similarly in a way that you have a longer time in the present region, but when the environment changes, then even if you spend a lot of time in your own region, it doesn't mean it's really good. So you can think of that like a simulation of age structure in an experimental case. And we just wanted to see how individuals are using this cue to direct their social information use. Yeah, so then we have this experiment, and then the next big step is formalizing the data generating process. So what we really want to do is we try to infer learning strategies from behavior. And doing that, we are faced with the so-called inverse problem. This means going from observed choices from data to hidden causes, to latent strategies. And that's a problem because typically many different empirical patterns can be, no, the other way around, many different processes can produce the same empirical pattern. So we cannot just rely on behavior and just compare rates of behavior across different situations, because they can be caused by many different processes. Instead, we can try to formalize the data generating process. So we can basically tell a story about how our data arose. And then we can use that story of how the data generated to simulate data before data collection, but then to analyze the data with the same model, and then also use simulation again to see how our model predictions compare to what individuals actually did. And so while the first model I showed you it's basically just philosophy with numbers, right? So the age-structured model, that's basically like a thought experiment. But now that's very, very concrete and predictive. So with this model, we really want to explain how the data actually arose. In the coming slides, there will be some math, but I will go through it slowly, and I just want to demystify the whole thing. So just show how it really works mechanistically. If you're not so interested in it, it's also fine. I will come back to the results later. But so what the model is actually doing is that it always estimates latent attractions or values for the different behavioral options. So each individual is characterized by some beliefs about which option is best at a certain point of time. And the model uses those attractions to then explain behavior. So the first basic building block of the model was how these attractions are updated in light of new experience. So the attractions in the next time step just equals the attractions of the previous time step plus the payoffs they experienced. And this parameter phi just weighs how important new incoming information is compared to previous attractions. So it's basically how fast individuals learn. So if this phi is 1, you just do whatever you got in the last time step. So you choose corn, and then all of a sudden you think corn is best. So that's clearly not adaptive. But if you don't, but if phi is very, very low, then you just never change your mind in light of new experience. But the second big building block is then how those attraction values and the social information of other individuals gets translated into choices. So we have an equation that says, so the probability to choose any one option I equals, then we have an asocial and a social choice probability. And this parameter sigma similarly says how important social information is compared to individual information. Then on the left, you can see the equation for the asocial probability, but that's just a softmax. So that's basically just a function that translates the attractions into choices and just rescales the whole thing. So the only thing that's important about this is this lambda parameter, which is basically their exploration rate. So, but it's not super important. So if lambda is low, then you behave very randomly or exploratory. You just try out a lot of stuff. And if lambda is large, then you always go with the option that you think is best, even if the differences are just very small. And then the social choice probability is composed of, again, 2 probabilities. So it's just these convex combinations all the way down. And I said in the beginning that we look at different cues. And here I implemented frequency-dependent learning. So this is a conformist learning, which basically means that common behaviors are disproportionately more likely to be copied. So if you're a conformist learner and you see that 2 of the 3 individuals chose a given option, then you are more than 66% likely to choose this option, right? Because the majority itself provides a cue that the information is adaptive. And so this is given by the parameter f, like this exponent. And that means, so if f is larger than 1, then you're attracted towards common behaviors. And if f is smaller than 1, then you're attracted towards uncommon behavior. So then you're basically like a maverick or an unconformist. You always go with the least common option. And then we also have this this other expression, which is just there for the experience bias. But all you need to know about this is that we have this beta parameter, and if beta is positive, then individuals are more likely to copy older individuals or more experienced individuals. And if beta is negative, then you're biased towards younger individuals. Yeah, and that's the full data generating process. And it's composed of data and parameters. And that's this very nice thing about Bayesian statistics, that data and parameters are basically the same thing. So you just have a joint generative probability model of all. And so we have the 6 different parameters that we want to estimate in the model. And then what we feed into it is, of course, the choices individuals make. and the social information they observe. Yeah, and then using this model, as I said, we can simulate new experiments, we can simulate new data. So here is an example. It's a simplified example with just two options, one on the bottom, one on the top. And I plotted both the choices individuals make and the attractions. So the attractions are the curves. The light gray option and the day, like the light gray and the dark gray regions, they indicate different regions. So remember, like the two regions on the different sides of a river, and the dashed lines represent temporal changes in the environment. Yeah, and but that's just for illustration. Like you can see, if, for example, if there's a lot of social learning, that's the bottom one, then individuals sometimes get stuck on the non-adaptive version. So you can see that right in the beginning, whereas the individual learner on the top converges on option one. The social learner in the bottom basically converges on option two, because likely many group members chose option two. So this individual got stuck with the maladaptive information. But on the other hand, as you can also see that social learning very often helps you change to different environments, especially if you migrate into another region. The individual learners, they're stuck longer with the previous option. So you can see it here. It takes them multiple rounds to try out the other option. But if you do social learning, then you can adjust very quickly after a change. It happens right now. So they migrate into another region, and now the blue line is rising, and they adjust very quickly. Whereas on the top, the more individual learner persists longer with their changes. So we can simulate just new data for this experiment, but then how do we actually use the model to infer strategies? And that's just one example. So as I said, the model continuously updates latent values for the four options. So in this case, the actor has a slight preference for rice, which is also what she chose in the previous round. And then in this round, she chose potatoes. And now the model tries to calculate which combination of parameter values is most likely to produce the given choice, potatoes, given the inferred latent values and the social information. So it basically takes so before we generated choices, right? Before in the simulation, we took the parameters as a given, and then we simulated choices from that. And now we just go the other way around. So we take the choices as a given, and then we estimate which parameter values are most likely to produce this choice, given the latent values and the choices of group members. So in this case, we can basically learn that the individual likely learned socially because she chose potatoes, although in her mind, rice was best at this point. And then she also likely was conformist in her learning because she adopted the most common behavior in her group, which is the potatoes, and she didn't bias her choice towards the most experienced group members, because in that case, she would have taken corn. And so doing that for all rows in the experiment and for each individual separately, we can basically learn a lot about the individual level learning strategies. And so we do that separately for each individual. And then we can just learn which parameter values were active in this individual. Yeah, and then as Ricardo said, so that was all done before the experiment was set up. And then I pre-registered this whole thing on OSF, but I found it difficult to put my experiment and the model into the standard templates they provide. So I basically just came up with my own text, which is not very optimal, I know, but it's still basically the Wild West with pre-registrations. There's so many different things you can do. And yeah, but in this document, I basically just described everything about the data generating process, then how the experiment looks like. So here I defined very precisely when all individuals numbered 1 to 8 are in different regions, how they switch, and the whole migration pattern. And then I also just laid out the predictions and the full analysis plans, just to have it out there. And it took me very long because I needed to learn the modeling, and I could have done that in parallel to data collection. But in hindsight, I'm really glad that we did it that way, because then it was so easy. Like, I just simulated the data and did the whole analysis. And then once the real experiment was done, I just needed to change the Excel files, basically. And then I could just run the same script on the real data. And I didn't have to make any decisions about what to analyze because they were already done in advance. Yeah.
So I guess that one of the things that happened always to me when I tried to do that is that as soon as my models meet the data, they fail in some, in hindsight, obvious way. But before, I couldn't have really predicted that, for instance, the variability of the single individual should not be that large or should not be that small in what I predicted. And I was just wondering if you could say a couple of words and on whether your models failed in some ways when you met the data, when you met the enemy, or whether it actually really worked nicely because you were really good at anticipating the parameters.
So right in the end of this talk, you will see a spectacular failure of the models. So now it seems like it will all be all good and nice, but in the end, you will see, that there is also a huge failure in it. So, but I think it's also just very important to pilot a lot. So I also I did a lot of piloting just to get a sense how real people behave. So I simulated the data and I tried to adjust the design parameters of the experiment. So the a number of rounds, the variability of in the multi-unbanded, I tried to adjust a lot of that just using simulation. But then in the end, I also just did a couple of pilot runs to be sure. But there's also ways in which the model fails, and I think that's as interesting, right? It's also very interesting to see how the model fails and why the model fails. But I will talk about that later. So one of the main things I wanted to figure out with the pre-registration and with the whole models was how do we make the learning parameters change over time? Because that's what I really wanted to know, right? So how individuals dynamically balance different sources of information. And there are endless ways to do this, basically, right? You could just have some linear models where parameters can just linear increase, or you can use like a sigmoid function or just like any functional form. But I thought that's a bit too constrained, right? Because I really want to pick up the behavior of individuals, and I want these functions to be flexible enough to also reflect sudden changes in behavior, and not just some very gradual changes as we could do with linear models. So the first thing I tried was to use monotonic effects. So here we just assume that the direction of change is monotonic. So it either increases or decreases over time, but the steps can be very abrupt. And so here that's just fitted on simulated data. The model estimates 2 parameters for each individual, which basically gives you the extreme values. So which is like the maximum and the minimum. And then we have those delta parameters, which give you the step sizes in which it changes. So that's just details. But so this delta sum part is a simplex, so it must sum to 1. And so you just multiply it basically with the difference, which is the effect, and that way you can get it on the outcome scale. And that model actually worked really well, but we're still imposing some sort of directionality, right? So this model just couldn't pick up any curves or any like U shape or something like that. So just to be sure, then I also implemented a Gaussian process regression, which is able to estimate any arbitrary function. So that's basically like a normal random effects approach, where we estimate different values for the different levels of experience. But at the same time, the model takes account of the fact that more similar levels of experience are more likely to show similar behavior. And what we're essentially doing is that instead of estimating the variance covariance matrix of the random effects directly from the data, we estimate a function that describes how the covariances change as experiences get more dissimilar. Yeah, so you don't need to get the details, but what's really cool about this is that we can fit any arbitrary function. So it could be whatever. And the model at the same time learns the values, but also the variance covariance matrix. And this example for in the plot, I simulated 2 different population of learners. So for one population, they were at like 0.4 social information use all the time, and nothing changed at all. And another population that as they moved into a new region, they do a lot of social learning. And then after roughly 5 rounds, they drop to 0 and they do no social learning at all. So those are the dashed lines. And I was quite happy with that. And the model could recover the broad patterns. But then, so that was one of the first failures of the model, because on simulated data, I could really do the full multi-level Gaussian process model, which is also a bit crazy. So I basically fitted one Gaussian process for each individual, which is each line. So that was really cool. But then on the actual data, that just failed miserably. So there was no way I could fit a Gaussian process for each individual. Likely because the data generating process was just not the same, right? Because with the simulated data, you really have a perfect equivalence between your simulated data and your analysis code. But with the real experiment, there is always some difference. So with the real data, I could just use the Gaussian process over all individuals, and I couldn't do the fully multi-level one, unfortunately. Yeah, and then after all that was done, we invited 237 participants into this nice lab that we just built up, and participants were paid between 11 and 14 euros, depending on their performance. And also at this step, there was just a lot of stuff happening because I built up this lab. So in the beginning, there were a lot of problems, of course. There were software problems where I just made mistakes. Then there were connection issues where I didn't make mistakes, but I was still very embarrassed in front of participants and I needed to send them home. So there's just a lot of stuff happening. Some participants were angry, drunk, anxious. You just have to deal with a lot of things. But then doing all that, I had some nice data. And here, it's really good to just look at the behavior first, right? Before doing all the fancy modeling, just as sort of a sanity check, just to see whether individuals behave the way you expected them to. So on the top, you can see just proportion of optimal choices after a spatial change and after a temporal change. And on the bottom, you can see how much social information they actually used. So that's from the mouse tracking data, right? So that's, we don't really know whether they really use the information to guide their choices, but that's just how much information they actually accessed. And quite predictably, they increased their performance over time, so they actually learned. But there is a difference between spatial and temporal changes. So after temporal changes, they start below chance level, which indicates that they persisted with their previous option. And after spatial changes, like already right after migration, they have a higher than chance probability to choosing the optimal option, which is most likely supported through social learning, as you can see in a bit. Yeah, so that's just behavior, and I was not too interested in that, just to have an idea of how they actually, like what they actually did and if it makes any sense. And so I was quite satisfied with that. And then next, I applied the model with increasing degree of complexity to the data. So first, I just use a basic multi-level model where parameters varied by individual, but they couldn't change over time. So they were fixed over time, but they were different per individual. And so what's interesting here is that there was evidence, like quite clear evidence for a strong conformist bias. So overall, individuals were more likely to bias their decision-making towards common options. And they also learned from older individuals, so from more experienced individuals, because the fold posterior is above 0, which means the model is quite certain that overall individuals bias their decision making towards more experienced individuals, which makes sense. But then what's also quite interesting is that we can then use the individual level parameter estimates and correlate them with the overall payoffs that individuals receive, just to see which parameters were actually adaptive in the experiment, or what was good to do. And we can see quite clearly that especially the weight of social learning was positively correlated with payoffs. That means that individuals who did more social learning were better in the experiment. And that's likely because a lot of individuals just also learned individually. So they just paid attention to private information. So there was a lot of information there at most times, so that social learning could actually be adaptive. And then also individuals who had a low exploration rate, so who were quite deterministic in their choices and who updated their learning quickly after changes, were also collecting more points in the experiment. Yeah, but now to the actual interesting part. So in the first model, I just compared how learning parameters change after temporal versus spatial changes in the environment. And we found that individuals rely substantially more on social information and were also more conformist in their copying after spatial changes in pink compared to temporal changes in green. So as predicted by theoretical modeling, after migration events, the population generally has higher proportions of adaptive behavior than after temporal changes. So in these circumstances, it makes sense to learn socially, which is also what we found. And also migrating individuals were especially conformist, because conformity can use as a tool to pool information from different individuals very quickly and quickly and reliably adopt adaptive behavior. But then after both types of change, individuals were more likely to copy experienced individuals. And that was quite unpredicted, because after spatial changes, it makes a lot of sense to copy the experienced individuals. But after temporal changes, everyone gets non-adapted at the same time, so it doesn't make any difference. So I was predicting, or the models were predicting, that after a spatial change, they should attend to experience cues, but after a temporal change, they should not attend to experience cues. But the model says that after both types of change, individuals just went with the higher numbers and always copied older individuals. I implemented the full time varying model, so where parameters could dynamically change over time. And so that's first the results for the monotonic effects models. And here each line represents a different individual, and the black lines just show the averages. And then we can see that while rates of social learning, so that's the first plot A, rapidly decline in rounds following migration, individuals remained relatively conformist to group typical behavior. So also the conformity exponent F slightly decreased, but it always stayed above 1. So even the resident individuals were still conformist in their copying. So we can basically see this pattern where migrating individuals use a lot of social learning and are conformist in their copying. And then the resident individuals, they rely much, much less on social information in general, because they know a lot about the environment. But when they use social learning, they're still conformist in their copying. And that basically lets them filter out non-adaptive variation, right? Yeah, and then we can also see adaptive changes in the asocial learning parameters, so in the learning rate, in the exploration rate, but that's very expected. So that's plot E and F. Yeah, Ricardo?
Yes, so I can see that there's different amounts of variability according to the parameters, right?
Yeah.
In particular, the individual variability in learning rate is astounding.
It's huge, yeah.
So do you have any intuition or reflection about why, while the other ones, there's still a lot of variability, but not the whole spectrum? For learning rate, that's not the case.
Yeah, so that's definitely an interesting point. So really, as you can see with the learning rate, there are some individuals who are just very, very quick in updating their behavior, and there are others who basically don't learn at all. So that's what it means if you have the learning rate close to 0. I think there's just some individuals who perceive the environment either as incredibly stable, so they don't change it, or they just are not motivated enough. I think that's very hard to tell whether it's an actual thing that they actually think the environment is so stable so they shouldn't change and they shouldn't update, or whether they just, or they just didn't. I think if you just choose the same option throughout the experiment, you will basically get a very low learning rate. But individuals were incentivized to actually learn because they could earn more money. And as far as I can see, most individuals actually tried. And I think I don't think there was a single case where people just like click through it without without trying different options. So yeah, but it's very interesting in the learning rate, the variability is huge. It's true, but it's just like, it might also be that it just, for example, compared to the exploration rate, because the scales are just very different, right? So a difference in the exploration rate between 0.5 and 20 is also huge. Like the consequences for behavior can also be really, really large, right? So you cannot directly translate the variability on the parameter scale to the variability in the outcome scale. So I think especially for the exploration rate, there is also a lot of variability, but it's just because it's a log link. So for the exploration rate, we use a log link function. So it just explodes the variability on the actual behavior outcome scale. Yeah, and with the social learning, for example, there's just this one individual up there with so much more attending to social information compared to anyone else. I think that's also quite interesting. Yeah, and then finally, I try to validate the model. We saw before using the Gaussian process regression, which doesn't assume any functional form, which is really nice. And you can see that the patterns hold up quite nicely with some interesting detail, but that's just very reassuring that the monotonic assumption that we made for the previous models didn't constrain the behavior at all. So there seems to be some increase in learning rate, for example, in the end, but there's also a huge error. There's a huge uncertainty in the model. So I wouldn't give too much on that. And then finally, so what I already announced, that then we used the fitted parameter estimates, but I didn't just use the parameter estimates. But so in the multi-level model, how that works is that the model estimates a latent distribution of individuals, right? So it basically says, okay, you gave me 200 participants, and from these 200 participants, I now estimate how those parameters are distributed in the population. And this distribution also contains all the covariances among the different parameters. So I use this inferred population of people to produce new individuals. And if I use the exact same parameter setup as I used in the model, and I plot the proportion of optimal choices, it looks something like that, which is very, very poor. So yeah, so that's somewhere in the appendix. I still refer to it, but I'm not proud of it. Yeah, so the general patterns are there, but they just learn very, very slowly. And only if I increase the differences between optimal and non-optimal options. So here I just doubled the difference. So in the actual experiment, the difference in points was always 3. So the optimal one, let's say 16, and the other one 13. And here I doubled the difference. So it was always 6. And with that, I reproduced the patterns very nicely. So I was really impressed by that. So the top row shows results from the normal multi-level model without the time varying parameters. And on the bottom, you can see the results from the model with a time varying parameters. And you can really reproduce the basic pattern. So with the after spatial changes, we start above chance level. With the temporal changes, we are below chance level. And then we also reach a similar levels. So and that's what I said before, Ricardo, right? So this the model really failed at this point. And what it tells me is that individuals, they were just not using pure reinforcement learning. But they were just assuming that one option is maybe best. And then they were doing something like Bayesian updating, where they were just using their points to infer which option is optimal at each point in time, instead of just doing pure reinforcement learning with the payoffs they get. So I think that just explains why the overall learning rate is much slower. And I would really like to do some more realistic models of learning, so that go beyond reinforcement learning and do something like variational inference or something, but that would be a whole different approach. But that was, yeah, so that's what the simulation then told me, that the overall patterns were very nicely reproduced by the simulations, which tells us that the model learned a lot from participants and can produce the same patterns, but we just need to make it easier for the model to have the same behavior, right? So we need to increase the difference between the different options just to make it easier for the model to pick up which option is best.
Can I follow up on that?
Yeah, sure.
Well, I guess that it's, in a sense, it's very close to the machine learning problem of one-shot learning, right? It seems that you can just put the real people straight in the situation and they can bootstrap much faster than the reinforcement learning model, at least, right?
Yeah, exactly.
And just the very last question on this slide is, I think in the real data you had a difference between easy and hard phases, which is not reproduced here, right?
Yeah, that's just because if by increasing the difference among, if you go math. Yeah, so there, if you look at the curves, right? If the means are quite close to each other, the distributions, they can't really overlap. But as you just move them away, I think then the variability within doesn't really matter anymore, right? Because then it will always be something like around 20 for the one and around 14 for the other one. And there is still variability, but the variability just doesn't matter as much anymore.
Thanks. Yeah, that makes a lot of sense.
Yeah, so then I'm also almost at the end. So what did we learn from this model? We saw that individuals strategically adjust learning over time. There are systematic differences between spatial and temporal modes of variation. And so there's been a lot of discussion in the literature about why individuals underuse social information in these experiments. So there was also a recent paper discussing multiple reasons why individuals don't learn as much from social information as they should. And I think what this experiment shows is that social learning is actually used extensively when it's most useful. So that's directly after migration, when you enter a group where social information provides a lot of quality information, but they rely more on personal information when they have either gathered enough information themselves. So if they've been very long in a region, or when the group members are also not expected to provide adaptive information. So this is after temporal change. So I think that's a very interesting thing, and it also relates back to the whole age structure point, right? That social learning is just much more useful if you have this whole demographic effect of like cultural information building up over time, right? And then if you're a newborn and you just enter a population where there's been generations of cultural learning, then of course social learning makes sense, right? But in all the models and experiments, you're just thrown in there. Everyone knows the same. Everyone is in the same situation. And then, of course, social learning doesn't make too much sense in these situations. Yeah, and then we can also see how stuff like between group cultural variation might be maintained by learning, because both migrants and residents are very conformist in their learning in this experiment. So the residents, even if they don't rely on much social information, if they do, they are still conformist. Yeah, and that was basically it. So I have a last slide about application of similar models to birds, but I might skip that because we're an hour. Yeah, and then in the end, I just want to thank my two great supervisors, Anna and Richard, and thank you for your attention. And yeah. Please just any comments, questions, complaints. I'm happy to chat.
So thank you. This was really a great talk. I'll be coordinating questions. So if people want to even just write a Q in the chat, that probably would be a good way of coordinating that. I have lots of questions, but I'll let other people speak first. I think Ralph Corvas.
Yeah, thanks, Dominik, for a fantastic talk. I wanted to ask like a main difference between your experiments and how you've been introducing it with the Rogers paradox is that strategy is not frequency dependent in terms of their payoffs. As if I followed your experimental design correctly, in the sense that if everyone plants grain, everyone will do better if that's the highest payoff. What would happen, do you think, to the dynamics once you would introduce such frequency dependence in your experiments, in the learning rates in the model? Is it something you've been thinking about?
I think we have the same trade-off built in the model, but it's just the case that enough individuals learn individually, right? So there is some, because in the experiment, we don't really evolve learning strategies. What happens in the Rogers model is, right, we have different generations, and then we evolve learning strategies over time. And I think in this experiment, I don't really expect that people figure out optimal learning rates within the experiment, right? They just come in with some preconceived strategies they learn from somewhere else, and then they apply it in the model. So I think there is the trade-off between individual and social learning, but there's just a lot of, but we just like to remember this plot of Rogers paradox, right? So we have one snapshot, right? We have one snapshot in this scenario, and if we could systematically vary how much individuals learn individually versus socially, I'm sure we could get some very interesting results. But yeah, so maybe you could actually like cue participants into being more individual or social learners in the experiments and see how that works out. But yeah, so I think the trade-off is built in, but we cannot really show it directly because yeah, we cannot evolve learning strategies in the lab.
Yeah, thank you.
So I'll go with the different questions, also on the lines of, why don't you go back and rerun 10 different lines of experiments with this slight variation? But I was recently reading the book, The Human Swarm by Moffat, who argues that a lot of our social learning and cultural evolution might actually be driven by social identity. Right? And in this setting that you've designed, it's kind of hard to maintain your social identity because there's the isolated migrant that goes to the new society and is, has to survive there on its own. I was wondering, like, what would happen if you actually had small groups of people that have interacted with each other in advance, and they sort of know and see that move into the new area. So I'm thinking, for instance, of the anecdote that when the Italians moved to Sao Paulo in Brazil, even if the ground is great for coffee, they just kept cultivating vine grapes for generations, and it's terrible wine, but they just keep on doing that. So I was wondering how social identity could play in these things, creating different stratifications, for instance.
I think that's a really, really interesting point. So we're basically trying in these experiments to get rid of all that stuff, right? Because we have it that learners are anonymous, they don't really know each other, and it's really like a stripped down version that wants to get at like the adaptive design. And it's all about, and that's also why we incentivize people, right? So we incentivize them so that they don't just do some random stuff, that they don't just be like, yeah, I like potatoes, we're the potato group, so let's go for the potatoes, which I expected much more Germans to do, right? But there was actually like, there was a slight overall preference for potatoes, but it was not very strong. But yeah, but we're basically trying to get rid of all that stuff. And I think it's a very, very, very interesting question. But the whole concept of social identity and ethnic markers, how they evolve, right? It's like an incredibly intricate relationship between learning processes and other social processes. I think it's definitely like super interesting, but I would expect just a lot of like much more hoarding behavior, right? So much more sticking, much more, yeah, just sticking with like unadaptive options. But it might also make sense because there is a lot of theory that says that ethnic markers are exactly there because they allow you to, because it structures cultural information, right? But that always works with coordination games. So I think if you have coordination games, but then ethnic markers are very adaptive to structure interactions in an adaptive way. But I'm also not sure in like that sort of model whether I think ethnic markers wouldn't make sense, but of course, ethnic markers evolve in a different context, in the context of coordination games, and then they might also be used in like those more social learning experiments. But yeah, it's definitely interesting, but I cannot say too much about it.
Thanks. I might have a follow-up, but I'll let Nicky Valentin give his question first.
Thanks for a very interesting and dense talk. To sort of follow up on Ricardo's question, I was wondering, because you could imagine many scenarios in the real world. This is a sort of one scenario that you've made up that have certain characteristics. Could you speculate a little bit on where in the real world you would find similar dynamics?
That's a very good point. So the models, they're sort of designed not to match the real world, but more to match the models, right? So the experiment is basically designed in a way that we can apply theoretical insights to the experiment, which is not a good reason, of course. But I think, I mean, like multi-armed bandit problems are everywhere, right? So I think that's also why they're studied so commonly, because like you can imagine different pizza places in your city, you know, and you go to one pizza place and you try the pizza and it's very, very good. But then what do? Do you switch to another pizza place, which might be even better, but then you might fail miserably and you go somewhere that's really bad, right? And so I think these exploitation trade-offs that are in these multi-armed bandit problems are very ubiquitous. And then it's also, and then social learning, I mean, you could hear from different people going to different pizza places, or you can see the recommendations and the revisions on Google, and you like integrate them in some way. So I think it's relevant as soon as you have some sort of exploration trade-off. If you have variability in payoffs and you try to figure out which one is optimal. But of course, like the time scales are very different. But that would be my answer, I guess.
So then I'll have another question, since nobody else is popping up yet in the chat, which is, I might have misunderstood, but you say that you were tracking where people were moving their mouths in order to reveal the information. So have you also looked at the behavior in which kind of information people looked at which frequency, and how much that impacted their choices?
So I didn't record the full search histories, like the full cursors, because I thought that's just unnecessary information. So I basically tracked at time points when individuals move into a box and when they leave the box. And so we can calculate like how much time they spend in each box. And so I used the information from the mouse tracking to condition only on information that participants actually access, right? So I used it in the learning models, and I just fed in the choices that they actually saw and not all of it, because right, it wouldn't make sense to assume that they were biased by some group members if they didn't even see it. But I have not yet analyzed the full search trajectories. And the main reason is that I am not really sure what to expect, and I'm not really sure what theory to use, right? Because I could theoretically do the full information search and under which conditions they look in different like options and how they, but I think one problem with that is also that the experiment was self-paced. So we moved forward to the next round when the slowest individual chose their option. And then there was some queue, like, and they would have been forced to move. But I think it's just like there's a huge variability in how long each round was. And I think that's quite difficult to account for, but I'm sure there are ways, but I was just not really sure what I would actually expect to see from these patterns. I had this idea, I was like, that would be really cool to have some visualization and to see how they acquired information. But yeah, I mean, if you know of some like good theory and something I could use or some framework I could use to model that instead of I just know information foraging theory and stuff like that. But yeah, with social information, I'm very happy for suggestions, to be honest.
I don't have any mechanistic model, but there is a lot of work on, for instance, social motivation. So you could look at whether the tendency to extensively look at all the others' choices and experience would reflect how much then the participant actually uses that information, right? Mm-hmm. Where if I check all three, I might have a higher rate of social learning and a higher rate of conformity mm-hmm. than if I tend to only check a couple, for instance. But I don't know how much they actually vary in that behavior, the participants. But yeah, that's definitely an interesting question to think about. Thanks. Mm-hmm. I think Ralph has another question.
Yeah, I wanted to ask. I mean, if I think about kind of like the shining examples in biology about, let's say, cumulative culture, or I would say that many of the examples we find where we say, oh wow, these are really kind of like individuals where we see some elements of cumulative culture that are very often quite long-lived animals, where you have, for example, killer whales who live for a long time, and where the older matriarchs take the lead in where to forage, for example. Same with elephants, right? So these are very long-lived animals. And when they rely a lot on the older individuals in these groups is actually when the conditions get harsh, right? So in these awesome killer whales, there's some beautiful examples when there's very unpredictable food availability. Then actually it's when the old matriarchs shine and when the whole group follows them, right? So in terms of time scales, like you actually need a long time to actually kind of capture the environmental unpredictability in itself and then make use in an adaptive way on that. Whereas you seem to treat environment unpredictabilities on somewhat different time scale, saying, oh, wow, we now have a very rapid once change. And that means all my previous information is actually kind of, redundant. Mm-hmm. Can you kind of, because I think you also, talking about humans and I think relatively long-lived because you want to have age structure, right? How do you kind of see this tension?
So this effect was basically made impossible by the way the model was set up, because in this model we had an infinite state environment. So every time the environment changed, we basically assumed that this state has never been there before. And so for this effect that you mentioned to work, we need to have some sort of reversible case, right? Like if you just imagine two different environmental states, just switches from 1 to 2 and back and forth. And I think then we could definitely have this effect where older individuals then become adapted again just because the environment reverts back to an old state, to like a stage that they have seen before, but the others haven't seen before. And I think that would be like a very straightforward and very nice extension to this model, I think.
Mm-hmm. And that, to me at least, that makes also biologically maybe a lot of sense, at least when looking back at, okay, there's now a shift in different climates, or I mean, maybe now with man-made, the acceleration is so fast that it's really hard for any individual to keep up. But you could argue that kind of looking back over many years and having memory of that actually is a very powerful source to deal with uncertainty, right? That it has been observed before, maybe these events. So yeah, biologically speaking, I think that also will be, would at least is a realistic scenario to keep in mind. Yeah, but I don't see how that building that in would allow that. Yeah, thanks.
Yeah, so and then there's also this other question of when, like, or if individuals can actually sense a change in the environment and how they can sense it, right? Because then you can have a lot of meta strategies, because then they can actually figure out the variability of the environment, or they can get estimates of how variable the environment is. And then there are a whole other, like, for example, if you're a learner who always learns socially, but then you learn only individually when you think the environment has changed. I think then that would definitely outcompete pure individual and social learners, because right, if you just can do it when it's useful, But I'm not even sure, like, I think even that wouldn't resolve Rogers' paradox. I'm not really sure, because that also doesn't increase the fitness of pure individual learners. And that's what needs to happen in order for the paradox to be solved. Yeah, but with the model, I think there is just different. I mean, that's the basic trade-offs between more like analytical and more simulation models, because a lot of the assumptions we did for the model were just to be in line with the old Rogers model, but also just to be able to do some actual algebra, right? And to get some analytical results back. And so I think that's really a question. I mean, I did some simulation to extend it, but there would have been like many more complicated things I would have been able to do if you wouldn't have chosen the setup that allows analytical tractability. But at the other hand, then we can have some really nice results and some really nice insights from that. So that's always a bit the trade-off between more realistic simulation modeling and more, yeah, a philosophical proof of concept mathematical models.
Yeah, I mean, I think that's also the great thing that you can actually think of kind of like different social structures or social learning mechanisms that we observe in the wild from different species and relate that back to their ecology via your equations, right? That you say, oh, wait, but if I take this assumption, then this strategies would actually roll out as optimal. And yeah, in an ideal world, that links to the ecology of these species, right? So we have learned something about the evolution of these strategies and why we see the diversity in social learning strategies. So yeah, no, really nice work.
I think with different modes of variability, it's quite straightforward, right? That you could imagine a population where there's a lot of spatial structure, a lot of different habitats. And so I think for some cases, even though like I described it as more philosophy with numbers, in some cases it can make some empirical predictions as well, I think, especially with like sources of variability and where the variability comes from and things like that.
Yeah, cool. Thanks very much.
Are there other questions?
Maybe I'm just going to ask one clarification question. You called the great apes an evolutionary dead end. What do you mean with that?
I mean, if you look at all different primates, the great apes are actually not very successful. You know, like if you want to build a successful primate at the moment, like the baboons, you know, baboons, they spread all over Africa. They're very successful. And the great apes, they're basically limited to very narrow habitats. They're just not very flexible. And that's also the tragic thing why like anthropogenic climate change and the reduction of their habitat is so like dangerous to their survival. So they're quite specialized. I mean, they do a lot of social learning. They are incredibly brainy animals, but they still seem to be very confined to very narrow habitats. And a great thing about, or the very interesting thing about humans is that like we take the great ape life history like even further, right? We develop even slower. We're even like, without culture, we would be so doomed to like small environments. You know, if you look at invasive species, invasive species usually have very fast life histories. You know, there's a very like a quick turnover, and I think that's the interesting thing about humans, that we that great apes in general are not very flexible in terms of different environments, and we take the biology of the great apes even further, but with all this culture thing, which of course co-evolved with the life history, we are able to make a great ape life history a big success story in terms of invasive success. And I think that's like the basic tension we need to explain there.
Yeah. Well, I agree with it, with the observations. Yeah.
So nice. So thank you again, Dominik. This was really great. Both the talk was very impressive and the discussion, I think it was really well managed, and I think a lot of good ideas came up. I guess we can declare the IMC meeting closed, but if you want to hang out and talk a bit more, I'd be happy to.
Yeah, so thanks.